Now we're going to talk about a sine wave. So remember, simple harmonic motion, sinusoidal motion, and uniform circular motion are all the same thing. If you look at these three circles, what are the similarities and the differences among their projections? Well, each projection is the same shape. The unifying constant is the sine angle, but the projections have different sizes or different amplitudes of displacements. The magnitude of the displacement varies with the size of the wheel, but the general shape of the three projections, the three waveforms, is the same. So what's the constant feature that characterizes all three of these projections? The sine of the angle. If you remember way back to high school, the sine is the displacement over the radius. The ratio of x to r is constant for any given angle. The sine of the angle is constant. The sine of a 45-degree angle, regardless of the size of the circle, will always be 0.707. Again, looking at these three circles, the sine of a 45-degree angle, regardless of the radius, regardless of the diameter, the sine will always be 0.707 for 45 degrees, or 1 for a 90-degree angle, or 0 for a 180-degree angle, and so on. The sine remains constant. So now let's redraw the displacement as represented by the sine. So the heights of the projection are now shown by the sine instead of the displacement. Therefore, it's now constant for each of those circles. The result is three superimposed curves which reveal what is constant about uniform circular motion, even though the motion can occur along circumferences of different sizes. If you were to plot all of the signs in the previous slide, what would happen? What does this look like? A sinusoidal waveform. So again, we have uniform circular motion or sinusoidal motion and simple harmonic motion, all representing the same thing. The common element in this example was the sine of the angle. It is for this reason that simple harmonic motion can also be graphed as sinusoidal motion, and the projection or the graph of simple harmonic motion is also called a sine wave, a sinusoidal wave, or just a sinusoid. So there are a number of names for the same thing. Finally, how can rectilinear motion be represented as uniform circular motion? So what this picture is we have our circle with its 360 degrees at the left. We then have a piston representing straight line motion, completing one full cycle of vibration from 0 degrees, pushed inward to maximum displacement at 90, pulled out back to equilibrium at 180, to maximum displacement in the opposite direction at 270, and finally back to equilibrium. As the circle moves, the piston will move in and out and in and out, creating a cycle of vibration. and that piston is pushing air forward to a balloon. The balloon is at equilibrium. Then when the piston is pushed 90 degrees, the balloon expands. Then as the piston is pulled back to equilibrium, it shrinks. And then as the piston is pulled all the way out to displacement in the opposite direction, 270, it really shrinks to nothing. So the balloon is going through these periods of equilibrium to maximum displacement, back to equilibrium, to maximum displacement in the negative direction, and finally back to home. It's completing 360 degrees of rotation, as is the circle, as is the piston, and what's happening is the balloon is pushing on the air molecules around it, setting up periods of compression and rarefaction, and sending out those sine waves.